Okay, welcome back to Learn RAS. In this episode, we're going to be talking about 2D model sensitivity. And to start off this conversation, we're going to contrast the differences between a 1D hydraulic model and 2D hydraulic model. So if you're familiar with 1D hydraulic modeling, you're probably well aware that a 1D hydraulic model will typically respond to or be sensitive to things like your cross-section spacing, your placement and orientation of those cross-sections. The 1D model is going to be responsive to how you use ineffective flow areas, obviously Manning's n values. The 1D models will respond to your contraction and expansion coefficients, and even things like HTAB parameters. Now, 2D models, by contrast, will respond to different things because the 2D models are kind of fundamentally different than the way a 1D model is set up. So a 2D model will respond to things like your mesh arrangement and things particularly like things like your cell size, the way you use breaklines or refinement regions to arrange your mesh. 2D models will also respond to Manning's n values, much like a 1D model will. Um, but because 2D models are inherently going to be unsteady state, you've got a host of computational parameters that can affect your model results. So particularly when we talk about the different equations that we can use in HEC-RAS for a 2D model, between like a diffusion wave or the full momentum equations, those are going to affect your 2D model results. But also things like your time step, Courant number, can affect the stability of your model, perhaps affecting the results, as well as things like a theta weighting factor as well. So for this example, we're going to be doing a quasi-steady state 2D model. When I say quasi-steady state, what we're going to be doing here in this example is running up a flow hydrograph until it achieves kind of a steady flow condition here, and looking at how the model, the 2D model, is going to respond to different model parameters. So the first thing that we're going to explore here is the sensitivity of the 2D model to the cell size. So we're going to try first with a 350-foot nominal cell size, then a 100-foot cell size, then a 25-foot cell size for our grids. We're not going to use any break lines for this first example here, and we're going to run the diffusion wave equations. So running this model with 350-foot cell size, you can see a few things with the results here. You can see the cell faces and things like major roadways aren't necessarily picked up when we don't have the break lines and we have a larger cell spacing. So you can see how the flow actually appears to be moving through these roadway embankments, where in reality there's probably going to be some obstruction. We would expect the flow to contract and expand in areas like this. When we move to a 100-foot cell size, you can see that the mesh is going to pick up some of the high areas of the roadway embankments, and you're going to start to see more of an expected flow pattern where you've got that contraction down to the bridge opening here. We're still getting a little bit of flow that appears to be leaking through the embankments, but we're starting to get a more expected flow behavior just by reducing our cell size, giving us a higher resolution in our mesh. When we move all the way down to a 25-foot cell size, you can see even more how the flow pattern contracts the flow through the bridge opening. We're not getting any more leaking across that roadway here. And you'll notice how at each iteration, we're starting to get a little bit more inundation with that higher resolution mesh, because we are picking up some of those areas where flow wouldn't be able to bypass. So by just refining our mesh resolution, we're actually we're allowing the model to produce higher water surface elevations, more inundation, because it's actually seeing those areas that would be barriers to flow. So when we look at a profile view of the maximum water surface elevations along the stream channel, what we can see here is that the 350-foot cell profile has the lowest profile for most of the reach here. As we move to the higher resolution, the 100 foot, we're getting a little bit more of a higher water surface elevation along our stream reach here. And then even more so with the 25 foot mesh, we're seeing the highest water surface elevation profile using that higher resolution mesh, particularly where we do have those flow contraction areas that the lower resolution mesh isn't quite picking up. Next thing we're going to explore is using break lines for our channels and for our banks. So what you can see here is we have kind of a perched or kind of a built-up channel bank system here. This is obviously a channelized ditch, but you can see that there's kind of a interesting perched banks here, and we want to try and capture that with some break lines here. So on the left, we're showing just the mesh without any break lines enforced. On the right, we're showing the mesh with break lines enforced along the channel and the banks to kind of pick up those perched banks for this particular stream. So what we can see here is the flow pattern, the particle tracer for both scenarios. Where we don't use the break lines, you can see that you're pretty much simplifying the flow to just be all in the downstream direction, even though there's some areas of high ground along those banks where flow really can't easily interact with the channel. The 2D model is kind of simplifying the flow pattern there. Where we have the break lines enforced, you can see how the model really is starting to pick up a better representation of the flow pattern. You got flow in your channel, and then when there's a low area where flow can interact with the overbanks, you're getting flow that moves laterally away from the channel before moving downstream again. So you can see how that interaction looks different and more realistic when we've enforced break lines into our mesh along the channel and along the banks. So using our 350 foot cell mesh and comparing how the break lines affected those results, you can see that the darker blue line here is just the 350 foot grid without the break lines. The teal line here has the 350 foot grid with those break lines along the channel and the banks, and you can see how that's caused a higher water surface elevation because it's really forced the flow interaction between the channel and the overbanks to be more controlled to where those overflows would actually be happening, and doesn't allow flow to bypass those high banks unless that flow elevation is exceeded in the channel. So that's why we're getting a higher profile using those break lines in our mesh. In the downstream area, we're getting a little bit of interesting behavior. I think I used a normal depth downstream boundary condition. So once the profiles and the model starts to settle out upstream of that downstream boundary condition, we can see how that flow behavior with those break lines has affected our flow profiles. When we try this, the break line comparison on our 20-foot cell mesh, you can see that we're still getting a little bit of a higher profile when we have those break lines enforced in our channel and our banks. But the difference isn't as drastic with the 25-foot mesh. And the reason for that is the 25-foot cell mesh is already picking up some of that interaction between the channel and the overbanks, just by nature of having a higher resolution mesh with that 25-foot cell size here. So we see a bigger difference when we've got that 350-foot cell grid when you add those break lines in the channel and the banks, more so than we see with the higher resolution 25-foot cell mesh. Next thing we're going to look at here is the impact of structure break lines on the results here. So you In this image on the left-hand side, you can see that we've got our 350-foot cell mesh. We've got our break lines at the channel and the banks, but we don't have any break lines enforced along the roadways. So you can see how the cell faces kind of span the roadway embankments that aren't picked up. And then on the right-hand side, we have the roadway embankments picked up through break lines here. So when we compare the results, what you can see here, again on the left-hand side, is that the particle tracers show that the model is basically allowing flow to move through the roadway embankment and not necessarily constrict down to the bridge opening because of the lack of a break line or cell faces along the roadway embankments. When we do enforce those break lines here on the right side, you can see that we do get that flow constriction here where the roadway is not overtopped. So flow is forced to move through the bridge opening and not move across the embankment. Here at this upstream roadway where the roadway is actually being overtopped, the model still allows flow to move across or over that roadway embankment. Here when we look at the 25-foot 25-foot cell mesh here, we're not seeing as big a difference here because, again, with the higher resolution mesh, the cell faces are already somewhat aligned and falling on the roadway embankment. So we're already seeing a pretty realistic flow behavior here where flow is being forced to constrict through the bridge opening with or without a break line when we have a higher resolution mesh to start with. So looking at the profile comparison again here, what we see is with our 350-foot mesh, that once you get to these structure openings, that's where you start to see the real deviation in the profiles, with the higher profiles coming where we have enforced those structure break lines with this teal line here. The darker blue line is the 350-foot mesh without those structure break lines. So you can see how having those break lines really allows the model to really see those head losses that are occurring due to the constriction, the flow constriction, because of the bridges in the 2D model domain. Here with the 25-foot cell, we see basically no difference between the profiles between using break lines at the structure and not using break lines at the structure, again, because that higher resolution mesh is already picking up that high ground from those structure embankments as is. So now looking at the comparison of the 25-foot versus 350-foot meshes with the break lines, what we can basically see from this is that using a nominal 350-foot mesh pretty much produces the same results as a higher resolution 25-foot mesh when we've enforced break lines for the channel and the banks and the structures. So that's what this is showing us here, is that whether we use a higher resolution mesh or a coarser mesh, as long as we have those break lines set up in the areas in the model where those are needed, particularly for the banks, the channels, the structures, we pretty much achieve the same results, with the exception of this downstream boundary condition, which again I mentioned is probably due to the fact that I used a normal depth. If I could have done this again, I probably would have chosen to use a known water surface elevation to start with, so we get consistency for all the comparative runs. But once that model runs upstream a little bit and things converge, we're seeing an identical profile for both conditions here. Last thing we want to check or test for sensitivity is the difference between the equations that we can use for our 2D models, the diffusion wave equation versus the full momentum equation. Just as a little bit of a refresher on the differences between these two equations, the diffusion wave equation will ignore the convective and local acceleration terms of the full momentum equation. So really the only remaining terms in your equation for the diffusion wave are the gravity term, the friction term, and the pressure term. The full momentum equation will really account for all the forces affecting the flow, but is generally going to be less stable computationally. It's going to require a lower Courant number, which means a smaller time step, which equals much longer model run times. The diffusion wave equation is going to be more computationally stable and can handle larger time steps, which will equate to shorter model run times, but may be less accurate if those local or convective acceleration terms control the flow. So when should you be using the diffusion wave versus the full momentum equation? The HEC-RAS user guide or hydraulic reference includes some applications that are going to be best suited for the full momentum equation. So this comes directly from the RAS guidance documents. But generally, you're going to want to use the full momentum equation when you have a very dynamic flood wave. So that's a classic example of that would be a dam breach scenario where anytime you've got a fast rising and falling hydrograph where you're going to have significant acceleration both spatially and in time, you're definitely going to want to use the full momentum equation for those situations. Where you have real abrupt flow contraction expansion within your 2D model, that's going to be best handled by the full momentum equation. This one might be a little bit counterintuitive, but when you have very flat sloped rivers, generally less than 1 foot for every mile, you're probably going to want to use the full momentum equation when you've got those really flat situations. And the reason being is that when you have a really flat sloped flow situation, your gravity and your friction terms are going to become very insignificant. If you've got a very slow moving flow, you're not going to have a lot of friction losses. So potentially your local and convective acceleration terms could be much more substantial than any of the gravity or friction terms. So a very flat slope river is a situation that you might want to consider using the full momentum equation for. Anytime you have wave propagation where you've got flood control, gate changes, for example, full momentum is best to use for that. If you've got super elevation at stream bends, if you need detailed velocities or water surface elevation distributions at like a bridge or some sort of hydraulic structure, the full momentum equation is going to give you the best look at those detailed 2D changes in velocities and water surface elevations along those type of features. Whenever you've got mixed flow regime transitions like a hydraulic jump, again, this is going to be best handled by a full momentum equation run. So when I tried this model with the full momentum equations, my first pass on this, I got profiles that looked like this. And just for reference, the pink profile here is the 25-foot mesh with the break lines using the diffusion wave equation. These bluish lines are the profiles that I got using the full momentum equation using the different mesh cell size resolutions. So what I was able to see from this initially is that I clearly had some stability, at least in one of my profiles, but then I had some really odd profiles further downstream in the model. And so when I first looked at this, I wasn't quite clear to me what this was, whether this was instability. It seemed unlikely that it was a hydraulic jump, but it wasn't clear to me what this was. So I had to do a little investigation to figure out what was going on with my full momentum equation runs. And using kind of an outflow, looking at the outflow hydrograph, I was able to confirm that what I was really seeing here was a form of instability in the model. You can see this kind of oscillation here in the flow, the outflow here, which is kind of a telltale sign of model instability. So I had to diagnose what this instability was being caused by, and there's a few different ways you can kind of diagnose that in the model using RAS Mapper. First, I looked at the water surface elevation grid, and what it showed me is that in the overbanks, I had a generally gradually transitioning water surface elevation But within the channel, that's really where I was seeing that those dips and those rises in the water surface elevation profile, and you can kind of see that here. I wanted to check the Froude number to see if I was getting any supercritical flow to kind of rule out the possibility of hydraulic jumps. And what the Froude grid showed me that was that the flow was well below a Froude number of 1, meaning that I really had entirely subcritical flow, no supercritical flow at all here. So there really wasn't a hydraulic jump that would be expected within this reach. I went to verify the Courant number and found that the Courant number for the entirety of the area was well within acceptable ranges. So it wasn't caused by a time step issue. It was being caused by something else. And it wasn't until I started looking at the velocity grid that I started to notice some odd things here. You can see that the channel velocities here are substantially higher than the overbank, which isn't entirely unexpected, but to see the velocities this much higher was a little bit surprising. And then particularly once I zoomed in and took a look at the velocity distribution, I was seeing some asymmetries in the velocity distribution, even though this is a pretty uniform channel. And what I noticed was that the mesh actually had kind of an asymmetrical grid, asymmetrical kind of meshing pattern within my channel. And so you can kind of see how this is affecting a little bit of the velocity distribution here. So I realized the problem actually was in how the mesh was set up within the channel. And really the reason the mesh was asymmetrical within my channel was due to the fact that I had break lines set for both my main channel and my left and right banks. And when I had set these up, I had originally had the enforce one cell protection radius set up for not only the water line, but the left and right bank. And so enforcing that one cell protection radius with break lines that were all set really close to one another caused the mesh to give me this odd kind of pattern in here. So what I did to fix that was I checked off the enforce one cell protection radius for the left and right bank break lines, and only left it on for the main channel waterline break line. And then I reinforced my mesh and got a much more symmetrical mesh, as you can see here. So on the left, we're seeing the old asymmetrical mesh. On the right, we're seeing the newer, improved, more symmetrical mesh here. And we're seeing the full momentum velocity distribution here. And we can see that it's a much more uniformed, much more expected velocity distribution here. And it's not as high a velocity in the channel, as it's not showing the same instabilities that it was before. So we fixed that, and what you can see here is the fixed full momentum equation profiles here. So the pink, the blue lines here, these are the 25-foot cells with the break lines. Actually, the pink one shows all the break lines. The dark blue shows only the channel break lines. The blue one has no break lines. This is all in the 25-foot mesh. And then this teal one shows the one that had the mesh with the asymmetrical channel in it. So you can see how once we fixed the channel, we got more of the expected flow behavior. But you can again see the sensitivity of the various break lines, even with the full momentum equations, and what that had, the effect that had on the flow profiles here. When we look at it with the 350-foot mesh, again, we're seeing the same kind of expected behavior with the break lines. The highest profile here in pink is the 350-foot mesh with the break lines enforced at the channel, banks, and structures. The dark blue is showing only the channel and bank break lines. The darker blue is the 350-foot mesh without any break lines. So you can see how That's the impact that breaklines has on the water surface elevation profiles here. And just to show a visual comparison of the diffusion wave results from the full momentum results, here we've got the flow moving through the bridge opening with the diffusion wave equations applied. When we move to the full momentum equation, what we start to get is we start to get these eddies on the downstream side of the bridge here, where flow is expanding again. You get that circular flow pattern that really can only be simulated using the full momentum equations and can't really be achieved using the diffusion wave equations. So here we're contrasting the full momentum equations using the 25-foot, 100-foot, and 350-foot cell size with all the break lines applied. And what this is showing us is that outside of the kind of downstream reach where we've got the boundary condition kind of influencing things, really we get the same flow profile with all these meshes once we've enforced all of our break lines. So we're really achieving pretty comparable results by enforcing break lines, even on a very pretty low resolution 350-foot cell size mesh. Comparing the full momentum and the diffusion wave equation results, this is on the 25-foot mesh with all the break lines enforced. So again, this is our most detailed mesh with all the break lines. You could see that the teal line here, this is the diffusion wave profile. The blue line is showing the full momentum profile. And what we're seeing here is that the full momentum profile jumps up higher where we've got those flow contractions at those bridges. So here's one of the bridges, here's another one of the bridges. You can see the full momentum will simulate more of those hydraulic losses going through those openings than the diffusion wave equation does. Once we're kind of outside of those bridge regions, the full momentum and diffusion wave profiles look fairly comparable, where we don't have those abrupt flow contractions. So just to give you a sense for the how those different models performed with the various run times, we could see with the 25-foot cell resolution meshes, we had over 200,000 computational cells. With the 100-foot cell size, we had about 20,000 cells. With a 350-foot mesh, we had 6,600 cells in our mesh. Using the diffuse wave equation, that 25-foot mesh took about 13 minutes to run. We had very minimal volume errors for any of the simulations, so volume error wasn't an issue for any of the different meshes or simulations we performed. When we went to a 100-foot diffuse wave run, we had a runtime of about 1 minute. Using the 350-foot mesh, we were able to complete a full run in 22 seconds. Now, when we move to the full momentum equations, that's where we experienced the longer run times. With the 25-foot mesh, we had about a 3-hour run time. When we had the 100-foot cell size, that full momentum equation was about 14 minutes. With the 350-foot mesh, that full momentum run took about 5 minutes to achieve. So just wanted to revisit this this comparison again. This is the 25-foot full momentum equation profile shown in the teal here. This blue line shows the 350-foot diffuse wave equation profile with all the break lines enforced. So again, this is showing kind of the difference between the mesh cell sizes and the different equations. You can see that again where the bridges are, where those flow contractions are, that's where we're seeing the biggest differences. When we're not influenced by those flow contractions, the results don't differ all that much. They're pretty comparable, but where you do have those big flow contraction areas, those are where you're going to see bigger differences between the full momentum and the diffusion wave equations. So some key takeaways here is that the mesh cell size is less significant once you have proper break lines set up. So by selectively adding detail to your mesh, you can really optimize your runtime efficiency with accuracy. You don't necessarily need to go to a super high resolution nominal cell size. If you can selectively add break lines where you need that detail in your model or refinement regions, you can really optimize your run times with accuracy. Break lines for your channel and your banks may be needed when the channel and overbank dynamics are complex. In this particular example, we had a channelized ditch with these built up banks. So that enforcing those break lines along those banks really showed some complex channel overbank flow interactions. So that was important to have, and it had a fairly significant impact on the results by enforcing those. Always remember to review your grid after you enforce those break lines, because having some asymmetries, particularly in your channel, could be problematic, especially when if you're running the full momentum equations, as we saw earlier in the presentation. The full momentum equations are generally going to produce higher water surface elevations, particularly if you've got abrupt contraction and expansions within your model. So, if you're debating whether or not to use the full momentum or the diffusion wave equations in an application where you could justify using the diffusion wave equation, it's probably a good idea to try running the full momentum equation and see what differences those show you, because you might find that there's some slightly higher elevations, particularly if you've got some abrupt contractions at various points within your 2D domain. It's worth noting that calibration is always going to be better than just sensitivity analysis. It's important to understand how the 2D models are going to be sensitive to various parameters. But for instance, at the bridges where we're seeing more head losses using the full momentum equation, it doesn't necessarily mean that was a more correct answer. The best case would be if we actually had some high watermarks or actually measured data that we can use to calibrate our model to. It seems to me that you could calibrate the model even using the diffusion wave equation to get reasonable ratings, particularly at bridges, if you have that information available. So don't just assume that the full momentum equation is going to give you the best answer. Having data that you can use to calibrate is, in my opinion, always going to be superior than just using the most detailed meshes and model equations. If you have that calibration data, you may be able to have some simplifications within your model that you can verify against observed data. So hopefully this was helpful to see some of the ways that 2D models are sensitive to various parameters. Leave a comment or a question if you have any, and subscribe if you want to see more content like this. Thanks.